faced with questions like this in the world of teaching and learning. Numbers help here. This is the world of measurement, the world of tests, the world of examinations, the world of surveys, and all of these generate numbers. But the real question is, how do we interpret these? Well, what about measuring educational performance? How accurate is any test or examination? Reveal true abilities. Is the group of learners typical? Or did they have an off day? Was the examination a fair test? It's a more difficult thing to measure educational performance. And this is where probability kicks in. We've often wondered questions like this. Was it a fair pay? Did I do myself justice? Was I at my best? Probability starts to become important. So let's look at this area of probability. Two classes of students. But are they different? Did the second class actually perform better, or was that just chance? Probability helps us to answer that question. What about this one? Last year, 43%, but this year went up to 47%. In general, it'll just be no difference. It's just random variation. So is it a real improvement, or was a difference you might expect just by elements of chance? Probability helps us. If we want to get answers, the bigger the sample size. How many do we need? It depends on the statistic you're using. Here's a simple rule of thumb. So we need reasonably big numbers to remove the element of chance. And you rarely get big enough numbers in a school to make comparisons year on year. Just look for a moment at this graph. Along the bottom, the examination marks are plotted. The number of students who get each mark is plotted. We know that most of our students get kind of average marks, so it comes to a peak in the middle. And there are only a few students who get very, very high marks or very, very low marks. This is known as a normal distribution because that's what you tend to expect if you make measurements of anything, including exam marks and tests. There's our average mark. Statisticians call that a mean. There's a measurement of the spread of the marks. Statisticians call it the standard deviation. But this kind of distribution is very common, and it's important to know whether we have it or don't have it, because it affects the statistics we might choose. There are ways of expressing probability. Try to make sense of this. If we are 95% confident that something didn't occur by chance, we write it that way, p less than 0.05 or p less than 5%. If we're 99% confident, we write it that way. If we're 99.9% confident, we write it that way. These levels of confidence are the ones that statisticians use simply because they relate to that normal distribution curve that I showed in the previous slide. And it's expressed in this way. And if we're not 95% confident, then we tend to think of it largely happening just by chance. The element of chance is too high. Numbers, what statistic do I use? What can help me to make sense of the numbers? There are three stages. But in this presentation, I want to focus on the first one. What statistic do I use? I'm only going to look at three broad areas here. Before we start, we have to ask two important questions. Given a lot of data, what question do you want to answer? And secondly, what kind of data do you possess? Now, I'm going to focus particularly on the first question. Let's look at some questions we might want to answer. Let's give an example. Suppose we've got a big set of marks. Do we want to know those who perform well in history also perform well in English? Here's another question. Two groups of students, perhaps taught in different ways, or perhaps taught last year with a different curriculum or a different approach. Did one group perform better than the other, or was it just chance? And what about their opinions of learning, which leads to their motivation and desire to learn? Does one group differ from another? Let's, for example, look at attitudes towards the sciences. Are girls more positive than boys? Statistics can help us here, but we have to choose the right statistic for the task. Here are three statistical processes: correlation, the t-test, and chi-square. Sounds a bit like mumbo-jumbo. That's the symbols that are used. Small r, small t, the Greek letter chi, squared. Correlation, the values run from -1 to +1. The other two, you can get values from 0 upwards, and in fact in the t-test, depending on how you do it, you can get negative numbers as well. In the first one, a high positive value indicates that the two things are related, a positive association. In the second two tests, just the higher the value, the more likely the result is to be significant. In other words, not caused by chance. We'd use correlation to answer the first question. We would use a t-test to answer the second question. And we'll use chi-square to answer the third question. We'll look in subsequent presentations a bit more detail at each of these tests. We need to be aware that there are 3 methods of calculation, and any good computer program will do any of the 3. It just requires us to tick the right box. And in fact, it can do all 3. But there are limitations, and that depends on the kind of data. And the limitations are expressed here. You need to use the right method for the right kind of data. When it comes to the t-test, there are several different kinds, and it's worth checking with an expert before you start. Chi-square, there are 2 types. Depending whether there's a control group, one that's just taken as normal, or there's no control group if you're comparing boys and girls. That is a bit more complicated. It's important to talk to an expert, someone who knows about this, before you gather your data. Is it going to be analysable, what you get? And then when you've got your data, ask them to show you how to do it. That's a way forward that will help us. But I hope this removes a little bit of the mystery.